Okay, related to the probability, you know that the graph of 2 to the negative x squared, at least if you've done the homework, which I expect just about everybody has done, because you all have been really good about that, the graph looks something like this, doesn't it?
Yeah.
Okay? Very much like a bell-shaped curve. Okay? Make sense? So you got a homework problem on the bell-shaped curve. I think, pretty sure. Now, related to probability. Okay? The graph of e to the negative x squared over 2, e is just a number. Okay? Limiting value of what you do if you compound interest n times and take the limit as n goes to infinity. Okay? So I can say e, you don't have to necessarily remember this, but it wouldn't hurt. This is the expression that you would use for the compound interest at the end of 1 year if your interest was 100% and you compounded it n times. If you understand compound interest, it's pretty easy to understand what that is. And if you can get 100% annual interest compounded continuously, invest your money in it if it's secure. Okay? You get rich real quick. You're not going to find that. Okay. Plenty of people that'll convince you that you will, so you better be careful about who you listen to. Okay? So just a brief blurb that relates to compound interest. But this function is very much like this function, right? The x is getting squared. Okay? Well, your graph is going to have basically the same shape. That dividing by 2 thing makes a difference, okay? And when you do this, now I don't have the graph drawn right. It should be a lot closer to the x-axis when you get over here, okay? But okay? Now, there's something I want to do today. I don't know if we'll get to it, but I hope to, because it's kind of one of my priorities. I'm going to have you roll steel balls at a target across the tabletop. There's going to be a piece of carbon paper in front of the target, and it's going to make a mark every time you roll the ball. Okay? So, you know, you're going to be to the right or left. You're never going to hit that mark exactly. Although, you know, if you're pretty good at it, you might get pretty close. Okay? If you get too close, we'll make it a little further away. Because you want to be able to measure how far you are. Okay? Well, the probability of being this far from the target is lower than the probability of being close to the target, right?
Yeah.
Okay? At least if your mean, if you're as likely to be to the right as you are to the left. Okay? So whatever 0 means, that might be the middle of your pattern. It might not actually be the target. So we can also measure how far the middle of your pattern is from the target. Okay? And it's going to be related to several things. Okay? And we're not going to get too deep into it. But the basic idea is this curve depicts the decreasing probability of being out here. Okay? So this is like And actually, I'm going to call this Z. I'm not quite using that term right, because Z, you'll be divided by the standard deviation. And 1 just represents one standard deviation. So you can find the mean of where you are. You can find the deviations. You can find the square root of the mean of the square deviations, right? So that's going to be related to the scale of your graph, okay? So, Z measures how many standard deviations you are from the middle. Then the probability of being at distance Z I'll make this more specific because I can with the trapezoidal approximation graph, because that's exactly what we use to analyze this thing. You've got the function, you can plug that into your calculator. You got an E button, just like you got the log button, okay? So, it sort of means the probability of being at distance Z versus Z. So it's like probability versus how far you are. That make sense? Okay, and the specific of it is simply that if you want the probability, now there's 0 probability of being at any exact number, right? You know, you got some real number, and there are lots more real numbers than there are fractions. Like you have 0 probability of landing on a real number. There's so many of them compared to the number of fractions, okay? So you have 0 probability of being at any point on the z-axis. But if you take some interval of the z-axis, okay? So here's your interval. Your probability of being in the interval is the area under the curve for that interval. I don't have room to write all that out, but I'll write it out more specifically when I assign a problem, okay? So the area under the curve for the interval over the total area. All right? So the probability, if you keep doing this, the probability that you're going to hit within this interval is this area divided by the total area. In this curve, essentially, there's very little area outside of the interval from -2 to 2. And if you go -3 to 3, you can just about disregard it, okay? So one thing I'll have you do is I'll have you take this function and do trapezoidal approximation, you know, 3 or 4 trapezoids on one side of the axis, because the other side is the same as this side, right? And figure out the total area. Okay? And there's a very specific expression for the total area that, believe it or not, involves pi. And where does that come from? Well, that's pretty deep in calculus. If you've had a really, really good calculus course for a year, you'd be in a position to understand. Okay? It's still a little bit beyond a first-year calculus course. Not much beyond. Not so far beyond that if you're really good at the end of the first year of calculus, you can't see it and understand it, but still pretty difficult. Okay. So I'll just give you that formula, but in the meantime, I'm not going to give you that formula. Okay? But we've got a constant out here, like an A term, right? Or an A factor that makes the total area 1. Make things easy. Okay? Very simple expression. Okay. Well, the whole idea is this is the normal distribution, and many, many things follow a normal distribution, including coin flips. Normal distribution is just the limit of what you get if you do a lot of coin flips, because you know your coin flip distributions look like this, right? Okay? Well, if you got a lot of flips, this curve is the one that fits. Okay? It's not hard to see. We'll develop that. You know, the whole idea, combinations, Pascal's triangles, that's pretty simple. And a little surprised you haven't seen combinations. But, you know, that's something, as I say, it's often seen like in 6th grade. And people don't necessarily remember it. Okay, so that's probability, because I keep getting questions about probabilities. So out of that question, we have this model, and we'll expand on that a little bit. Okay?